Good evening. So today we are in the week. We will solve the problem that regarding this week 8 classes and the week 8 assignment. Myself Subham, PMRF Department of Chemistry, IIT Guwahati. I am the TA for this course, and which is taught by Professor Sandeep Paul, Professor Department of Chemistry, IIT Guwahati. So I'll wait for 1-2 minutes for others to join, and after that we will start. Okay, we will start now. So first we will revise the formula, and after that we will solve the questions. So we will start with the formula. So first the partition function. partition functions. So Q, we denote it by Q, and we are going to discuss Q translational, Q rotational, Q vibrational, and Q electronic. And we know that partition function is multiplicative. So Q total is Q translational into Q rotation into Q vibration into Q electronic. And the energy that we got through it, E total, is additive. That is E translation plus E rotation plus E vibration plus E electron. Okay, so we individually now will study these whole partition functions. So now first Q translation is equals to 2 pi m kBt divided by h square to the power 3 by 2 into volume. So this is translational partition function, and we can write it as V by lambda cube, where lambda is de Broglie wavelength. So we know this, and lambda will become, so from here lambda is h upon under root 2 pi m kBt. Okay, so we will use this formula, and then Q rotational, this is equals to kBt by sigma hcb, and b here is rotational constant, which is equals to h upon 8 pi square ic. 8 pi square ic. I is moment of inertia and c is speed of light, and as is Planck constant. So we can write it in the form of T by sigma theta. So where theta is h nu by kb. Theta is rotational temperature. Okay, and sigma is symmetry factor. And value of sigma is equals to 1 for heterodiatomic gases. And it is sigma is equals to 2 for homodiatomic gases like H2, N2, etc., O2 extract, etc., and heteroatomic like CO, NO, etc. Okay. So after that we will discuss this vibrational, Q vibration. So Q vibrational is equals to Q vibrational is equals to e to the power minus beta E divided by 1 minus e to the power beta 2 e to the power minus beta E. So we can write it, beta is nothing but 1 over kBt. So this is e to the power minus h nu by 2 kBt divided by 1 minus e to the power minus h nu by kBt. So we have written here h nu because we know that for vibrational levels, the energy gap between for harmonic, in the harmonic case, the delta E is equals to h nu. So if we consider it as from 0, then it will is h nu to h nu and so on. And we know that energy is equals to, if we are not considering 0 point energy, then we are not taking 0 point energy as 0, then it is n plus half h nu for harmonic oscillator. Okay, and if 0 point energy is not 0, we are not taking it 0 because it starts from half h nu. E naught is equals to half h nu. Let's consider that E naught is equals to 0, then E will be n h nu. Okay, so addition function Q is equals to Q vibrational if E0 is equals to half h nu, means ground state energy is not, we are not considering it 0, then this is equal to e to the power minus h nu by 2 kBt divided by 1 minus e to the power minus h nu by kBt. Okay, and what if ground state energy we are taking it as 0? This is just ground state, we are taking it at 0, and then we are considering nh nu energy levels for n is equals to 0, 1, 2 and so on. N is vibrational quantum number, we can denote it by nu also. So nu is vibrational quantum number. Okay, and this nu is representing frequency. So now Q vibration will be equal to 1 over 1 minus e to the power minus h nu by kBt. So this is when 0 point energy is 0. Okay, now we can denote h nu by kB h nu by kB by theta, and then it will become 1 over 1 minus theta by t, and this theta is vibrational characteristic vibrational temperature. Now I made a mistake in rotational part. Q rotational is equals to kBt by sigma hcb, and this will be equal to t by sigma theta rotational, and theta rotational is equals to nothing but this hcb by kb, and this b is equals to h upon 8 pi square ic. So we can put it here, so it will become h square upon 8 pi square I into k. h upon 8 pi square IC, and C will cancel out. So h square 8 pi square I kb. Okay. So this will be co-rotational, and now we have also studied that value of Q vibrational for high temperature and low temperature. So we will see it again. Q vibrational, if 0 point energy is not equals to 0, then it is e to the power minus h nu by 2 kBt divided by 1 minus e to the power minus h nu by kBt. So its value at temperature T very low, very low, and T very high. Its value depend on the value of T, whether it is very high or very low. And if we denote it is in the form of e to the power minus theta by t, 2t, and 1 minus e to the power minus theta by t, we can say if t is low, then theta by t is very high, very greater than 1. So theta by t, if t is low, then this is very high, and this whole quantity will be very low. E to the power minus theta by t will be very, very less than 1. So at low temperature, Q vibrational will be e to the power minus theta by 2t, where theta is equals to h nu by kb. Okay. So now at high temperature, theta by t is very less than 1, then e to the power minus theta by t will be very, very greater than 1. So we can expand this in the form of e to the power minus x is equals to 1 plus x, 1 minus x plus x square by 2 factorial minus x cube by 3 factorial, and so on. So e to the power minus theta by t is equals to 1 minus theta by t plus theta by t square divided by 1 by 2 factorial, and so on, minus so on. So we can neglect these quantities, as we know that theta by t is very, very less than 1. So after this theta by t, we can neglect all the quantities, because its square will be very less. So we can, it does not make sense to take these very little quantities. So we can neglect these. So this will be e to the power minus theta will be e to the power minus theta by t will be equals to 1 minus theta by t. So Q vibrational will become e to the power minus theta by 2t divided by 1 minus 1 plus theta by t. Okay, so this will cancel out. So this is t by theta e to the power minus theta by 2t. Okay, so this was all about this vibrational partition function. Now we will solve this thermodynamics properties, that we are going to use in today's lecture as well. Thermodynamic properties. First of all, we will talk about this internal energy, and it is denoted by U or E also, and we know this is the function of temperature, and it can be written as U is equals to N kb T square curl by curl T of ln Q. Q is partition function, okay, at constant volume. And this is true for both distinguishable and indistinguishable particles. This formula will apply to both. We can further solve it for like, okay, now we will Cp and Cv we know, Cp and Cv, heat capacity at constant pressure, heat capacity at constant volume. So Cv is equals to change in curl by curl T of U at constant volume, and Cp is curl by curl T of H at constant pressure. We can solve these for, we know that for monoatomic gases, there are no rotation and vibration. So Q rotation and Q vibration will be 1. So we can solve Q total as Q translation into Q electronic. So rotation and Q electronic, and electronic for ground state electronic partition function Q is equals to G naught, as we know that it is summation of Gi to the power e to the power minus Ei upon kVt, and for ground state energy Ei is equal to 0, so it will be G e to the power 0 1, and Gi is G0, and this energy is 1 for such like let's consider hydrogen, so for that this energy is 1. So we can say that Q electronic is 1, so it will Q total will be Q translational only, and Q translational is nothing but 2 pi m kBt by h square to the power 3 by 2 into V. Okay, so this is Q total, and we can solve this Q total by putting this value in kBt square curl by curl T of ln Q, and we can, this is Q total, so this is Q total. If we derive this, we get U as 3 by 2 RT. This is for 1 mole. Okay, and we can write it as 3 by 2 nRT for n moles. This is the internal energy for 1 mole of monoatomic gas, and Cv will be 3 by 2 R. Okay, next we will solve it for others. Now we know that it is Cv is equals to 3 by 2 R for monoatomic gases. And if we consider the other gases, then we can calculate it for all the gases. If we solve q rotational, and we get the value of CV, that is equals to NR for n mole of gases. For n mole of gas, CV rotation is NR, and I will not solve these expressions, but I will write the formulas only. Q vibrational, for Q vibrational, it was CV of vibration is equals to 5/2 R if temperature is very less than theta vibration. Theta vibration is Hc upon Kb. So if temperature is very less, then it is 5/2 R, and it is very high, then it is, if temperature is very high, then it is 7/2 R, and normally it is equals to R into 5/2 plus 2 e to the power u divided by e to the power u minus 1. And what this u is, e to the power minus 1 square, what this u is equals to theta vibrational by T, the whole quantity, that Hc by kBt, this is u. So we get the value of Cv for vibration, rotation, and the this electronic and translation. So we know that for for translation it is Cv is 3/2 R, and Cv translation, Cv electronic we can neglect, and for Cv rotation it is R for 1 mole we are considering, and for Cv vibration it can have 3 value, 5/2 R, 7/2 R, or that we have this value. Okay, so like this we can calculate Cv. Now entropy, as not according to the formula of S naught, I will write here, and the expression I will not solve. This according to Shakur Tetrode equation, S is equals to NR ln e to the power 5/2 into kBt divided by pressure into lambda cube, where lambda is de Broglie wavelength, and this is equals to h upon 2 pi m kBt under root. So this formula is very important, and we are going to use this. We know that S is also equal to K ln W, Kb ln W. W is nothing but the states, microstates. Okay. Apart from this, we can calculate G, that is equals to H minus Ts. So we know S, we can calculate H by using this U plus RT is H. So we can use this H, S and G to calculate our calculation purpose we can use this formula. So next we will move to the questions probably, or we can also this a Helmholtz function, this is u minus ts. So we have one other formula for s, that is equals to after solving this square tetraid equation, we can get the s is equals to n kb ln q by n plus u by t plus n kb. This is for indistinguishable particle, and for distinguishable s is equals to n kb ln q plus u by 2 for distinguishable particle. By using these formulas we can calculate the other properties as well. So okay, now we are good to go with through the questions, and first I will solve the assignment questions, and after that I have some more questions, and then we will solve those questions. So first question, the molecular partition function of a system is given by qt is equals to kbt by hc to the power 3 by 2 into 8 pi square m kbt, this is kb. This is kb. At pi square m kbt by h square to the power 3 by 2, where the symbol have their usual meaning. The heat capacity at constant volume for the system is for 1 mole. So what we are given this q partition function, molecular partition function, and we have to calculate the heat capacity at constant volume, so for 1 mole, and we know that heat capacity is curl U by curl T at constant volume, and U is, we have just written the formula for U, that is equals to n kb T square curl by curl T of ln q qt, and for 1 mole it is this is for n number of particles. For 1 mole it will be n into kb, that is equal to r T square curl by curl T of ln q. So we can solve this equation and get the answer. First of all, we need ln q. So ln q will be ln of kb T by hc to the power 3 by 2 into 8 pi square m kb T by h square to the power 3 by 2. So this will be ln q is equals to 3 by 2 ln kbt by hc plus 3 by 2 ln 8 pi square m kbt by h square, and it's too thin. I will try to reduce the size. It is too much thick. so it is not changing. Okay, so this is 3 by 2 ln kBt by hc plus 3 by 2 ln 8 pi square m kBt by h square. Now we need to calculate the logarithm, differentiation of ln q with respect to temperature at constant volume. So this is 3 by 2 and ln this is equals to kBt into hc, and now the differentiation of this is equal to kb by hc plus 3 by 2, and this is 1 over 8 pi square m kb t into h square upon into, now differentiating this 8 pi square m kb by h square. So this is 3 by 2 hc kb will cancel out, h square this will cancel out. So this is 3 by 2 t plus 3 by 2 t, that is equals to 3 by t. Now now this we need to we have gotten this curl by curl t of ln q is equals to 3 by t. So now we need to put this value in the formula. This was 3 by t. So the formula of u is equals to n kb t square. Sorry, for 1 mole it is r t square curl by curl t of ln q at constant volume. So this quantity we have calculated. So need to put this value here, rt square into 3 by t. So this is 3 rt. So u we get. Now curl u by curl t at constant volume is cv, heat capacity at constant volume. So this will be 3r. So the answer is 3r. Now this is the second question. Consider a two-level quantum system with energies E1 is equal to 0, E2 is equal to E. The Helmholtz free energy of the system is given by, so we need to calculate A. That one formula I have not discussed there, that is A is also equals to minus n kb ln q. This was calculated by this thermodynamics properties only. So this is the value of A and kb ln q. So all we need to calculate the q and put the value here, and we'll get the answer. Consider two level system with energy. So they have not given any number of particles. So n is equal to, we will consider n is equal to 1 here, and partition function we have to calculate. So this is E1 and E1 is equals to 0 and E2 is equals to E. So we can write Q is equals to summation of Gi e to the power minus Ei by kBt. So this is G, this is not given, so we will consider it as 1. E to the power minus 0 plus e to the power minus E by kBt. So this is 1 plus e to the power minus E by kBt. The value of partition function. Then A will be minus kb ln 1 plus e to the power minus E by kBt. So formula minus kBt ln 1 plus e to the power minus beta e. So beta is this 1 over kBt. So we can, if we put here, this will be minus kb ln 1 plus e to the power minus beta e. This is the answer. Now to the third question. Consider a system of n number of non-interacting distinguishable particles. Okay. Where each particle can be in 3 energy levels. The lowest one, called the ground state, okay, is non-degenerate. Degeneracy is given. So this is G naught is equals to 1. For ground state, G naught is equal to 1. And we can consider E naught energy is equals to 0. And its energy is considered to be 0. Okay. The middle one at energy E is doubly degenerate. So middle one is G1, that is equals to degeneracy is 2. And we can say that E1 is equals to E. The highest one at energy 2E is triply degenerate. So degeneracy is 3 for the third energy level and the energy is 2E. Let's say these are 3 energy levels and with energy 0, E and 2E. Considering canonical ensemble, calculate the internal energy U. So we need to calculate U, and we know U is equal to kVt for n number of particles and kVt square curl by curl T of ln Q at constant volume. So first we need to calculate Q for this, and then taking the ln and then differentiate it. After that we will get the U. So I have to erase this. So now we will start for Q. So Q will be summation of Gi into e to the power minus Ei upon kVt, and we know that Q is equals to, for 0 energy state this is 1 plus e to the power minus, and degeneracy is 1 for not ground state, then doubly degenerate, so it is 2 e to the power minus G1 is 2, so e to the power minus E by kVt, and then plus e 3 triply degenerate state, and energy is 2E divided by kVt. So this is the partition function, and simply ln Q is equals to simply ln of this function. Now taking the we need to take the differential of this ln Q, because this we will put in the formula ln Q. Okay, so this will ln this is the differentiation of will be 1 over this quantity, this Q, 1 plus 2 e to the power minus E by kVt plus 3 e to the power minus 2E by kVt, and now differentiating all the terms individually. So because ln, if we consider ln A x and differentiate it with respect to x, then we first write it as 1 over x and then differentiate this ax. So this will be first this differential of this is equal to 1 over this quantity and then differentiating this quantity. So we apply this here also. Differentiate 1 with respect to time, temperature, this will give 0, and differentiating it this quantity, it will give e to the power minus same quantity firstly, and then we will differentiate this quantity, and this quantity will give E minus E by kV into 1 over differential of 1 over t is minus 1 over t square plus 3 into e to the power minus 2e by kbt into this minus 2e by kbt into minus 1 over t square. So now this is 2 into e to the power minus e over kbt into e upon kbt square, this minus and minus, this will be plus 3 into again minus and minus, this minus and then minus will be plus. So e to the power minus 2e upon kbt into 2e upon kbt square, sorry there is no t here, divided by 1 plus 2 e to the power minus e upon kbt plus 3 e to the power minus 2e upon kbt. So this is the value of curl by curl T of ln Q. I will solve it here also. Question 3. So we can take this e to the power minus e by kbt from constant from this is the here also and in this also, so we can take constant. So and this 2 is also here, so we can take 2 into e to the power minus e by kbt as constant. So curl by curl T of ln Q, this is equals to 2 into e to the power minus e upon kbt, and this e by kbt square is also here, so e by kbt square is also constant, then this will be 1 plus 3 into, and then 1 power is gone, so 1 will remain, so this is 1 plus e to the power minus e by kbt, because it was e to the power minus 2e by kbt, so I have considered it as e to the power minus e by kbt square, so 1 power is taken out and 1 power will remain, so it is like this, divided by this whole quantity 1 plus 2 e to the power minus e upon kbt plus e to the power 3 e to the power minus 2 e upon kbt, and there it was 3 here also. So this is the value of curl by curl T of ln Q, and we need to calculate this n kbt square curl by curl T of ln Q, that is equals to u, and we just simply multiply, we can convert it into this, we can multiply here with n into kbt square, so this kbt square will cancel out and the remaining part will be 2n e, this 2, this n and this e, and this quantity e to the power minus e upon kbt, and this quantity 1 plus 3 e to the power minus e upon kbt, and divided by 1 plus 2 e to the power minus e upon kbt plus 3 e to the power minus 2e upon kbt. So this is the answer, and we will match it here. 2ne into e to the power minus e upon kbt, 1 plus 3 e to the power minus e upon kbt, 2ne, so either this or this is not the answer. 2ne e to the power minus beta e, 2ne e to the power minus beta e, 1 plus 3 e to the power minus beta e, and then this whole 1 plus 2 e to the power minus e upon kbt plus 3 e to the power minus 2 upon 2e upon kbt, so this is also here. So this is the answer. 2ne e to the power minus beta e 1 plus 3 e to, okay, this is the answer. Now we will move to the fourth question. Considering the question 3, calculate the entropy of the system. Okay, so I have written that formula also. This S is equals to, in the previous slide, okay, I have erased it, so I will write it again. So this S is equals to, by solving this ST equation, this is N KB ln Q plus U by T. So we have just calculated this U and we know the value of Q, and by simply putting the value here we can get this S. So what was the Q? Q was 1 plus e to the power minus e upon kbt plus e to the power minus 2e upon kbt, and this 1 over kbt can be considered as beta. So this is 1 plus e to the power minus beta e plus e to the power minus 2 beta e. So this is the value of partition function Q. And now the value of U, we have just calculated U. U is nothing but this first option 2n e to the power minus beta e 1 plus 3 e to the power minus beta e, and divided by this partition function 1 plus 2 e to the power minus beta e plus, okay, 1 3 was there, then reason we see I have not written here, 2 and 3 e to the power minus 2 beta e. Okay, so we have U, we have Q, and we have this formula, so we can simply put the values here and get the answer. So S is equals to N KB ln Q. So ln Q is ln 1 plus 2 e to the power minus beta e plus 3 e to the power minus beta 2 beta e plus U was this quantity, so this will come here, and divided by T, this quantity divided by T. So you can match the answer. And KB ln, this was for n particle, no? Okay, and KB ln Q. So this is correct in all the three options. This is not correct. So now we will look for this U by T. So U was from the previous question also we have calculated this 2 ne e to the power minus beta e 1 plus 3 e to the power minus beta e divided by 1 plus 2. Okay, this one is looking correct, divided by T also. So this is part 1 is correct. Let's see other options also. 2ne e to the power minus beta 1 plus, okay, this is incorrect because this was 1 plus 3 e to the power minus beta. This one 2ne e to the power minus beta e 1 plus e to the power minus beta e divided by T 1 plus e to the power, okay, here 2 is not here, so this is not correct. So option 1 is correct only. So I will take a break for 2 minutes, and after that I will start from this question number 5. Okay, so we will start again with this question number 5. So the molecular partition function of a system is given, and it is given as Qt is equals to A T to the power 4. The internal energy of system is for 1 mole. So partition function Qt is equals to A T to the power 4. It is given, and we need to calculate the internal energy. So we have used this formula, and we will again use this formula. For 1 mole it is R, T square L by T of ln Q. So first of all we calculate ln Q, that is equals to ln of A T to the power 4, which is equals to ln A plus 4 ln T. Now we will differentiate it. L by L2 of ln Q is equals to ln A. Differentiation of ln A with respect to temperature is 0, and for ln T this is 1 over T. So this is for 4 over T. So ln Q is 4 over T. Now U is equals to R T square into 4 by T, that is equals to, we can cancel out this T, 4 RT. The answer is 4 RT internal energy. So option C is correct. Now to the 6th question. Consider a 3-level quantum system with energy E1 is equals to 0, E2 is equals to E, and E3 is equal to 2E. The Helmholtz free energy of the system is given by which one? So we know that A is equals to minus KB ln KBT ln Q for 1 mole, for 1 particle. So we just need to calculate Q here and put the value here in this formula and get the answer. So the energy levels are given. E naught, E1 is equals to 0, E2 is equals to E, and E3 is equals to 2E. And degeneracies are not given, so we can consider it as 1. So the partition function is summation of Gi e to the power minus Ei by kBt. So this is for 0, this is 1 plus e to the power minus E over kBt plus e to the power minus 2E over kBt. This is equals to E1 plus e to the power minus beta E plus e to the power minus 2 beta E, the value of partition function Q. Now putting this value into the formula, A is equals to minus KB T ln 1 plus e to the power minus beta E plus e to the power minus 2 beta. So this is the answer, and this is incorrect, and the option is B, minus kBt ln 1 plus e to the power minus beta E plus e to the power minus 2 beta E. Okay. So now we will move to the question number 7. Calculate the values of Cp naught, S naught, H naught. This is the standard molar quantities. This heat capacity at constant pressure, heat capacity, entropy, and this enthalpy, and gives free energy for H at 3000 Kelvin. So calculating the Cp is, this is the monatomic gas. Calculation of Cp is very easy. Cp is equals to, we know that Cv for this monatomic gas is 3 by 2 Nr. For 1 mole it is 3 by 2 R. And we also know for an ideal gas, if we consider as ideal gas, Cp minus Cv is equal to Nr. So for 1 mole it is Cp minus Cv is equal to R. Cp is equal to R plus Cv. And Cv is 3 by 2 R, so Cp is 3 by 2 R plus R. So this is 5 by 2 R. Cp is 5 by 2 R for a monatomic ideal gas. So we get the value of Cp naught here at standard condition. This is 5 by 2 R. And we can calculate it into kilojoule, joule per mole per Kelvin. So we can calculate this value. 2.5 into 8.314 is equals to 20.785 joule per Kelvin per mole. Now for this, first we can calculate this H naught. We know that this H naught, this is nothing, just this. We know that Cp is curvature of H. So from here we can get this. If we think like this, this Cp naught dt is equals to curl H. So integrating it, can get the value of H. If we consider from 0 to H, if we consider 0 enthalpy, so we know that this is 3 by 2 R, 5 by 2 is equal to 5 by 2 RT. From differentiating this only, we get this 5 by 2 R Cp naught. So H naught is 5 by 2 RT. So H naught is 20.785. This is 5 by 2 R into T. T temperature is 3000 Kelvin. So this is joule per mole. Just multiply it. 20.785 into 3000. This is 62355 joule per mole. Or we can write it as 62.355 kilojoule per mole. Okay. So we have H naught, we have Cp naught. Now we need to calculate this S naught. And we know that S naught is nothing but this. Wait a minute. Okay, where were we? Okay, now we again have to do this. So the value of Cp naught we have calculated, that is equals to Cp naught is equals to, okay, I'll see the answer I have calculated, so it is erased, so I have to look it again. This was 5 by 2 R and H naught was 5 by 2 RT. So again I will calculate it quickly. 2.5 into 8.314, this is 20.785 joule per Kelvin per mole heat capacity, and this is into 3000 temperature, this is 62.3 55 kilojoule per mole. This is del H naught. So we are calculating now H naught, and we know the formula of H naught is nR ln e to the power 5 by 2 into kb T divided by pressure P and lambda, which is de Broglie wavelength according to ST. So we'll just we need to calculate this lambda first. Lambda is nothing but the H upon 2 pi m kVt under root. So this lambda is H upon 2 pi m kVt under root. So we can calculate this value first and then put the value here and get the answer S naught. So this lambda is 6.626 into 10 to the power minus 34 divided by, and this is for hydrogen, so we know that mass of hydrogen is 1 gram per mole, which is equals to 1 upon 6.022 into 10 to the power 23, and it is grams, so convert it into kilograms. This is mass of one hydrogen atom. This mass of one hydrogen atom. So this is equals to under root 2 into pi 2 pi into m is 10 to the power 1 over 6.022 into 10 to the power minus 23. We can simplify this. 10 over 6.022. This is, we can write it as 1.66 into 10 to the power minus 27, because this is 10 to the power 23 plus 23, and when it go into this numerator, though it will be 10 to the power minus 26, and I have written 10 divided by 10, so this is 10 to the power minus 27, and 10 divided by 6 is 1.66, so I have just simplified this, and then kb 1.38 into 10 to the power minus 23 into temperature 3000. All units are balanced. Now solving this, So quickly I will solve this quantity with the calculator. 2 into 3.14 into 1.66 into 1.38 is equals to this, and into 3000. So this whole quantity is 6.626 into 10 to the power minus 34 divided by 4.3158 into 10 to the power 46 under root. So this is equals to, if we take 4.3158 under root, 4.3158 under root, this is 2.077, 6.626 divided by 2.077 into 10 to the power minus 34 into 10 to the power, this 46, this is minus 23, oh, sorry, okay, this was minus here, so this is plus 23. So 6.626 divided by 2.077 is 3.19. 3.19 into 10 to the power, and this is minus 11. This is the value of lambda. We can put this value here, and we can solve the value as not. This is R, n is for one number of moles, n is 1. So R is 8.314 by 800. S naught is equals to R ln e to the power 5 by 2 into kb 1.38 into 10 to the power minus 23 T 3000. And now this pressure, it is not given, but it is standard condition, so we can take it as 1 atm. For 1 atm is equals to 101,325 Pascal, that is Newton per meter square. So we need this unit in meter, that is why I am so changing, because this lambda we have got it in meter, so that is why I have changed it to meter. So now this is equals to, we can write it 1.01325 into 10 to the power 5 into lambda cube. Lambda is 3.19 into 10 to the power minus 11. So we can solve this and get the answer. ln e, we can write it as ln e to the power 5 by 2 plus all this quantity. So this will be 5 by 2, ln e is 1 plus, we can simplify this 10 to the power minus 33, and then we will go up 10 to the power 10, and then this 10 to the power minus 5, this will 10 to the power 5. So 5 ln 10 plus ln 1.38 into 3000 divided by 1.01325 into 3.19 cube. So just simply solve this. .38 into 3000 divided by 1.01325 divided by 3.19. So this whole quantity is ln 125. This will give 4.8. So this is 4.8, and this is 2.303 into 5. 11.515, and this is 2.5 into 8.314. So 2.5 plus 11.515 plus 4.8 into 8.314 is equals to 156.42. This is in joule per mole. This is the value of S naught. We need to calculate G naught. This is equals to H naught minus T S naught, and we have calculated H naught. Okay, this was 62.355 kilojoule. 62.355 kilojoule per mole minus T, temperature is 3000 Kelvin, and this is in 156.42 joule per mole. Okay, this was in joule per mole per Kelvin. So Kelvin cancel out. It will be joule. It is joule and it is kilojoule. So we need to multiply this side by 10 to the power minus 3 to convert it into kilojoule per mole. So now the units are balanced. So this is 10 to the power minus 3, and this cancel out these 30. So it is 156.42 into 3. This is 469.26. And this is 62.355 minus 62.355, and the answer is minus 406.905 kilojoule per mole. This is the value of G naught. So we get all the values: Cp naught, H naught, and this S naught, here it is, and this G naught. Now we will move to the next question. So it is the similar kind of question, but this we are going to solve for argon. Argon at 298 Kelvin and 1 bar. So first of all, we need to calculate S naught and then Cp naught. So S naught we will calculate this by using the same process, this formula, and then calculate lambda, and then inputting the values and get the answer. So S naught is R for 1 mole, R ln e to the power 5 by 2 kBt divided by P, pressure is 1 bar here, and lambda. So first we will calculate this lambda, which is equals to H upon 2 pi m kBt under root. So lambda is, and this m for this argon, this is we can consider 39.95. Okay, let me confirm this value. Even 39.95. okay, m is 39.95 joule per mole. and we can change it into, sorry, this is gram per mole. We can change it to kilogram. So this will be 39.95 into 10 to the power minus 3 divided by 6.022 into 10 to the power 23 kg. And we have solved it this is 39.95 into 1. We have solved for the hydrogen 1.66 into 10 to the power minus 27 kilogram. So we can put this value here. Lambda is equals to H 6.626 into 10 to the power minus 34 divided by 2 into 3.14 into 39.95 into 1.66 into 10 to the power minus 27 into 1.38 into 10 to the power minus 23 into temperature is 298. This is equals to this 10 to the power minus 27, 10 to the power minus 23, this is 10 to the power 50, and rest I will multiply. Into 1.66 into 1.38 into 298. This is 6.626 into 10 to the power minus 34 divided by under root of 1.71 into 10 to the power minus 5 into 10 to the power minus 23. So 10 to the power minus 50. And this is plus 10 to the power plus 5. So this is, you can write it as 17.1 into 10 to the power 4. So this will become 6.626 into 10 to the power minus 34 divided by 17.1 to under root, and this will be 10 to the power minus 23. So taking this under root, and this is 6.626 divided by 4.138 into 10 to the power minus 11, and this is 6.626 divided by 4.138, 1.6 into 10 to the power minus 11 meter lambda. We got the value of lambda. Now putting here and get the answer. S naught is equals to 8.314 e to the power 5 by 2, 1.38 into 10 to the power minus 23 kb, temperature 298, pressure 1 bar, that is equal to 10 to the power 5 Pascal or Newton per meter square, and then this 1.6 into 10 to the power minus 11 cube. This is equals to 8.314 ln, this is 5 by 2 plus this 10 to the power 5 and 10 to the power minus 33, this is 10 to the power minus 33 plus 10, and then 10 to the power 5, this is 5 ln 10, and this ln all quantity will multiply. 1.38 into 298 divided by 1.6 cube. So this is coming 100.4. So this was 8.314, 2.5 plus this is what the value of this 11.515, and this is 4.61. 4.61 plus 11.515 plus 2.5 into 8.314. This is equal to 154.84 joule per Kelvin per mole. Other quantity we need to calculate is Cp naught, and we know that Cp naught is just we solved it here. This Cp naught is equal to 5 by 2R. I explained it, so I will use this formula 5 by 2R. This is 2.5 into 8.314, that is equals to 20.785 joule per Kelvin per mole. Now we will move to the question number 9. Calculate the molar entropy of H atom at 1000 Kelvin at 1 bar and 1000 bar. So we need to calculate the molar entropy at this temperature for this and this pressure. So already we have calculated lambda for this H, and we will just quickly do it. First of all, we will calculate lambda and then put the value in formula S. So now we know how to solve this, so I will quickly do this. Two pi m is 1.66 into 10 to the power minus 27 kb 1.38 into 10 to the power minus 23 kb. T is 1000. Okay, so solving this quickly. 2 into 3.14 into 1.66 into 1.38 into 1000. This is 1.438 under root 6.626 under root 1.438 into 10 to the power minus 10 to the power minus 34, and this is 10 to the power minus 23. This is 10 to the power minus 46. The divided by 2 is 10 to the power minus 23. So this is equals to 6.626 divided by 1.199, or this is 1.2 only, into 10 to the power minus 11. 6.626 divided by 1.2, this is 5.52 into 10 to the power minus 11, value of lambda in meter. Now at 1 bar, S is equals to 8.314 ln e to the power 5 by 2 1.38 k T divided by pressure. This is in 1 bar, so this is 10 to the power 5 Newton, that is equal to 10 to the power 5 Newton per meter square, into this is 5.5 into 10 to the power minus 11 to the power 3, and we can calculate it for this 1000 bar. This is equal to 10 to the power into 10 to the power 5 into 10 to the power 5 3 10 to the power 8. This is Pascal or Newton per meter square. So putting this value also 8.314 ln e to the power 5 by 2 into 1.38 into 10 to the power minus 23. Temperature is 1000, and then this is 10 to the power 8 into this whole 5.5 into 10 to the power minus 11. So to the power 3. We need to solve these two quantities, and first I will solve this and then that. 8.314 ln this can be written as 5 by 2 plus the 10 to the power 5 and 33. This is 5 ln 10 10 to the power 5 ln of 10 to the power 5 is 5 ln 10 plus multiplying the rest 1.38 into 1000 divided by 5.5 cube. This is ln 8.29. So this quantity is same for both, so I will solve both simultaneously. So this is 5 by 2 plus, then this 10 to the power will change. This is 10 to the power 8, 10 to the power minus 33, and this is 10 to the power 10 divided minus 10 to the power 8. This is 10 to the power 2. So this is 2 ln 10 plus the rest quantity is same, ln 8.295 for. So simply solving this 8.294 ln, this is 2.115 plus this is 2.303 into 2, 4.606, and this is 2.5 multiply by 8.314. Here it is 8.314, 2.5 plus what was this value, 11.515 plus, and this is 2.115. So simply solving this 2.5 plus 11.515 plus 2.115 into 8.314, this is 134.10. 5 joule per Kelvin per mole, and it is 0.5 plus 4.606 plus 2.115 into 8.314, this is 76.66 joule per Kelvin per mole. So we can see that the value of entropy decreases with increasing pressure, and we know this also that the randomness, degree of randomness decreases with increasing pressure, and hence S value will decrease. So now to the next question, question number 10. The correct entropy for 6 identical particles with their occupation number is in 4 states is. So 4 states are given and their occupation number is given. So we need to calculate the entropy, and we know that S is equals to Kb ln W also. W is the microstate, number of microstates, and we know that for this kind of system W is n factorial multiplication of Gi to the power Ni divided by Ni divided by Ni, where Ni is the occupation number and Gi is the degeneracy. So total number of particles is 6, so 6 factorial. Since degeneracy is 1 for all, so we can just simply write it as 1. So this is 1 divided by 0 factorial, occupation number 1 factorial, 2 factorial and 3 factorial. So this is 6 factorial divided by 2 factorial, 3 factorial. This is equal to 6 into 5 into 4 divided by 2. So this is 60. W is 60. So entropy will be Kb ln 60. So Kb ln 60. This is the answer. Now to the question number 11. A certain system of non-interacting particle has the single particle partition function f. F is given by a v e to the power bt, where a is some constant. The average energy per particle will be. So we need to calculate average energy. That is also internal energy. So we know that internal energy is kBT square ln curl by curl T of ln q. Q is f here, so curl by curl T of ln f at constant volume. First of all, we will calculate ln f. Ln f is equal to ln a v e to the power bt, which is equals to ln a plus ln v plus bt. Now differentiating it at constant volume. This is constant, so 0, and volume is also constant, so 0. This is b only. Now putting the value in the formula, kb t square into b. So it is b kb t square. So it is b kb t square. So second one is the option number 2 is correct. Next question is, the first excited state of O2 is this, above the ground level. Calculate N1 by N0 at 25 degrees Celsius and 1500 Kelvin. So 25 degrees Celsius is 298 Kelvin. So we can calculate this. N1 by N0, we know that it is e to the power minus E0 by kBt and e to the power minus E1 by kBt. So it is given that it is 15.72 into 10 to the power minus 20 joule above the first excited state is above this amount of energy above the ground state. So we can write it as e to the power minus E1 plus E0 by kBt by considering it in numerator. So it is e to the power, if we take minus common and kBt common, so it is E1 minus E0 divided by kBt. So E1 by minus E0 is given, so it is exponential of minus 15.72 into 10 to the power minus 20 divided by 8. Okay, this is in joule. Okay, this is kb, so it is 1.38 into 10 to the power minus 23 into temperature is 298. So we can calculate this value. (15.72) divided by 1.38 and 298 is 3.88. Exponential of minus 3.88 into 10 to the power 3. So taking the exponential. Okay. Something is wrong. Showing error. Have we made any mistake? KB is 1.3 into 10 to the power minus 23. This is joule and this is joule per Kelvin and this is Kelvin, so it will cancel. It is all balanced. This is in joule and minus 23. This is 10 to the power 3. Okay, I will calculate it again. 15.72 divided by 1.38 divided by 298 is equals to, okay, it was, I made a mistake here. It is whole quantity, this whole quantity is 38.225 minus. So taking this exponentially, the value is 2.5 into 10 to the power minus 17, this N1 by N0. This is very less amount. So we can say that population of N1 with respect to N0 is very less at room temperature. Now we will calculate it for 1500 Kelvin. For 1500 Kelvin, N1 by N0, we just need to change the temperature here and solve this same exponential of minus, what was the value, 15.72 into 10 to the power minus 20 divided by 1.38 into 10 to the power minus 23 into this temperature is 1500. Temperature is 1500. So just need to calculate this. 15.72 divided by 15.72 into 1000 divided by 1.38 divided by 1500. This is minus 7.59. Exponential of this is equals to 5.03 into 10 to the power minus 5. So we can notice one thing, that on increasing the temperature, population of N1 with respect to N0 is increasing. This is 10 to the power minus 5 and this is 10 to the power minus 17. So it is increasing in a very considerable amount. So by increasing the temperature to the higher value, this can be changed. So population of N1 excited state can be increased by changing the temperature. So this is all I have for today. So if you have any question, you can ask now. If you don't have any question, you can leave. I'll wait for another 2 to 3 minutes and then I will leave the meeting. If you don't have any question, I will leave the meeting after 2 to 3 minutes. If you have any question, you can ask me now. Thank you.